Isabel, if you're here?
Yes, can you hear me?
We can hear you, yeah. We can hear.
Finally.
So I'll give you the lead up. Yeah, and we can see you as well. Very good.
So do I have the permissions for to move the slide?
You should, yeah. It works.
I don't think it's working.
Yeah. I don't know. I gave you control.
Yeah.
I gave you control, but if it's not working, I can move the slides for you.
I can try again.
Yeah. Try. Just I don't know, either with click or with the keyboard. I'm not too sure.
No, it's not.
Yeah. Okay.
Sorry.
You can just ask me to move the slides. No problem.
Okay. Thank you very much. Thank you, Anne. Well, good morning to everyone. Thank you for your presence here in this webinar. I am Isabel Lopes. I am a researcher at the University of Aveiro in Portugal. And today I will talk a little bit about the characterization of the impact on the environment of the materials and products that are being developed within Bio-Uptake, and this being done by using ecotoxicological tools. Next slide, please. So just a brief contextualization. As you are all aware of, the European Union adopted the Green Deal in 2020. And the main goals of this Green Deal is to achieve by 2050 the climate neutrality and also a prosperous and fair society. For this, and to support the Green Deal, many strategies and regulations have been implemented. I included here some just as examples: the eco-design for sustainable products, the Green Claim Directive, the chemical strategy for sustainable towards a toxic-free environment. But as I mentioned, there are many other strategies and regulations that support the European Green Deal, and all these regulatory landscape focus on a shift in the paradigm of the European Union that aims now to promote a sustainable growth and also a circular and bioeconomy. And within these concepts, the European Union challenges the industry to move from fossil-based materials into bio-based materials that are recyclable and biodegradable. And this is what you have been listening to in the previous presentation. So this is the context of the Bio-Uptake project. And next slide, please. Within all these directives, some of the targets that are common and to attain this sustainable growth is that the new materials to be developed, the bio-based materials, they need to be safer materials for the environment and human. They should move towards zero pollution for air, water, and soil, and promote the reduction of the pollution to levels that are considered no longer harmful to the health and the natural ecosystems, and thus creating a toxic-free environment. And to do this, we need to assess the safety and sustainability of these new products along the entire development and innovation process. So from the design to the final stage of the development and production of the products. And this safety and sustainability assessment involves many parameters, namely the quantity of water being used along the process, the emissions of gas that are involved in greenhouse, like the carbon dioxide, but and we'll talk about this in her presentation. But within these parameters, it is also important and mandatory by some regulamentations to assess the ecotoxicity of these new materials to the aquatic environment and also terrestrial environment. Next slide, please. Some of the regulatory landscape that frames this ecotoxicity characterization relates to the REACH regulation that requires the generation and registration of ecotoxicity data for the new chemicals, materials, composites, products that are being produced, for the materials and products that have a mixture of constituents. We also need to characterize the toxicity of those mixtures, not only of the materials, but also of the leachates of these materials. Then the classification, labeling and packaging regulation also uses this ecotoxicity data to classify the mixtures as hazardous or non-hazardous, and then based on this classification, the products are labeled with pictograms by the legal entities. And another regulation that also requires this ecotoxicity data is the Eco-Design Directive, since it requires that the product has a documented assessment of their environmental impacts, which includes ecotoxicity data. So the ecotoxicity data is really important to support the market access of these new bio-based materials and as well their regulatory compliance. Next slide, please. So within this frame, we did the ecotoxicity characterization of several materials within the Bio-Uptake project. As you already saw, this scheme, this project develops 3 main products, and within the streamline for each of these products, you can see here that there are a lot of raw materials, intermediate formats, and as well the final products. And we needed to generate ecotoxicity tests for these different groups of chemicals and compounds and materials. Next slide, please. Next slide, please. Okay, thank you. So all these materials and substances that were used within these streamlines for each product were grouped in 4 groups. The bioepoxy resins that included the bisphenol-free dicyclic ether of vanillyl alcohol, the PHTE. Then we had the bio-based fibers made of carbon and of wood that you already heard about them. The bio-based pellets, here the polylactic acid that was then benchmarked with fossil-based polymers like the polycaprolactone and also polyamide. And then we also tested the bio-based intermediate formats that were composed of the flax fibers and other of the raw materials that are here constituted. So for each one of these group of compounds and materials, we needed to implement different procedures. Next slide, please, to prepare the samples to then characterize the ecotoxicity of the substances, materials, and of the intermediate formats. So these different approaches consisted mainly of direct dissolution of the compounds, and this was done for the bioresins because we can directly dissolve them in aqueous media that is then used to perform the ecotoxicity assays. But then for the materials like the wood and carbon fibers and the pellets made of the different bio-based and fossil-based polymers, we cannot dissolve them in the water that is going to be used for the ecotoxicity assay. So we needed to produce leachates, and this was done according to a standard guideline that is mentioned here of TIN, by using 10:1 ratio, and then we needed to filtrate the eluate that was produced. And then for the intermediate formats, of course, we also cannot dissolve them into test media, so we also needed to generate leachates. But for this, the regulations suggest another standard guideline, that is the SEN, that uses a ratio of 8 cubic centimeters of the formats per square centimeter of the aqueous media. Next slide, please. So just briefly, I would just like to highlight here that sometimes dissolving the chemicals, in this case the resins, is not as easy as it seems, because they have particular characteristics that need to be taken into account when preparing the samples for the ecotoxicity assays. Specifically for the bioresins, we needed to prepare the stock solution into under an argon environment, because when in contact of oxygen, the polymerization of the resin sometimes is impaired, and then they immediately harden. And if this happens, then we cannot proceed with the toxicity assaying. So we needed to prepare them in this argon environment, and sometimes some of these resins are very hydrophobic, so we also need to use organic solvents to dissolve them, and only then we can prepare the stock solution, and then all the concentrations that need to be tested. The standard guidelines ask for at least 5 concentrations to be tested for each chemical or leachate. Next slide, please. Then just very briefly for the bio-based fibers and bio-based pellets, we, as I mentioned, needed to generate the leachates, the elutrates, and this is easily done by using this ratio of 10:1, and then leaving this mixture by stirring for 24 hours, and then we just filtrate the water and then dilute this water for the 5 concentrations to be tested in the acute toxicity assays. Next slide, please. Okay, and for the bio-based intermediate formats, the same. We need to produce the leachates in the ratio that is recommended by the standard guideline. And then in this case, for the intermediate formats, the standard guidelines recommends that we should test the toxicity of leachates with different stirring periods. So we tested after 24 hours after stirring, 32 days and 64 days, and this is done at room temperature. Of course, that for the bio-based materials, we also need to filtrate these leachates through 0.22 micrometers filters, and then dilute this eluate for the 5 concentrations to be tested in the ecotoxicity assays. Next slide, please. The ecotoxicity assays that are recommended to characterize the toxicity of the new compounds to aquatic biota is usually recommended to be done to at least 3 different taxa with functional levels and also trophic levels. Usually the ones that are tested in the first year of this process are the microalgae, here represented by Rhaphidocereus subcapitata, a primary consumer here represented by Daphnia magna, and the secondary consumer here represented by the fish Danio rarium. So this will be the minimum toxicity assays that are required. However, when running then the LCA, the framework recommends to use more species, because different species may hold very different sensitivities to the different chemicals, and so we need to be representative of the natural communities. In this sense, we decided to test 5 species that are here represented. So a microalgae, an aquatic macrophyte, the laminar, Daphne magda is already mentioned, then another primary consumer that is the rotifer Brachionus caliciflorus, and then your rare that is the fish species. So for each one of these species, we tested the 5 concentrations of all the raw materials, the bio-based materials, and the intermediate formats that I mentioned earlier. Next slide, please. And now I would like to show you some examples of the results that you obtain. I will not show all of them because it's a very large data set, of course, but just to highlight here some results that we obtain for you to have an idea of what we also concluded here regarding all these materials. So in this slide are the results that you obtained for the resins. The batch is a bisphenol-based resin, so it's not a bio-based. And then we have here Jiva, the PHT and cysteamine that are bio-based resins. And here I included the values of LC50. This is the concentration of the resin that causes 50% of effect in each one of these organisms. So if we have a value of, for example, 24.25 milligrams per liter, just to round it, and another one of 2, the one of 2 is more toxic than the one of 25, because we need a much higher quantity in the 25 to induce the same percentage of effect, that is 50%. So taking this into consideration, we can see in this table that Jiva, this bioresin developed within the Bio-Uptake, was the one that exhibited the highest values of LC50s, and indeed for Daniel Harry it had no effect. So this was the resin that induced the least toxicity for all these aquatic toxicity, for all these aquatic species, which of course is a positive result considering that we want to move to the bio-based materials. Next slide, please. Regarding the fibers, so the carbon fiber and wood fiber, here we have the same results, but here the unitary percentage, because remember that for this we tested the leachates, not the fibers directly dissolved in the aquatic, in the test media. So here we also have the LC50s, here is a D because it's the dose, the dilution. And what we could see is that overall, both the carbon fiber and wood fiber induce some toxicity to almost all the tested aquatic organisms, except for the carbon fiber that did not induce the significant effect on the growth of the microalgae. But these were interesting results because we could spot that the carbon fibers were overall least toxic to the aquatic organisms when compared with the wood fiber, which was probably related with the fact that some of these these wood fibers that are driven or are originated from wood waste, sometimes these wood wastes, they have some toxic materials like metals and that come from the inks, for example, that are used in these wood, and probably toxicity that we saw here was related with that. But an interesting thing, next slide please, was that the incorporation of these fibers into intermediate formats, the PAs, that you already also heard about them, we did not saw any toxicity in these intermediate formats that were composed by the wood fibers and by the carbon fibers. So here in these graphs, what you see in the first ones for the algae is the effects on their growth. So in the x-axis, we have the control and then the different dilutions, and you can see that the growth of the microalgae is equal along all the dilutions, both for the wood fibers and for the carbon fibers, meaning no effect. And then for the rotifers and for the fish, we also had no effects of any of these intermediate formats. So it is interesting to understand that even though we observed some toxicity of the fibers alone, when they are incorporated in these intermediate formats, the elements that can induce those toxicity are not leachate into the aqueous medium, so turning it safer. Next slide, please. And finally, as a final example, here I included some data regarding the polymers. So here we have two bio-based polymers, the PLA1 and 2 in green, and then the polyamide that is fossil-based and the polycrapolactone that is also fossil-based. And here I only presented the results for the fish and the rotifers because it's a lot of graphs, but for the other species, the pattern of results was similar. So here you can see that for the fish, the two bio-based polymers had no toxicity. For the fish as well, the fossil-based polyamide, but then PCl exerted some toxicity to the fish. And a similar pattern was also observed for the rotifer. But though for PLA1, we saw some small toxicity for the rotifer. But actually, these results indeed also suggest that PLA is less toxic than fossil-based. And regarding, for example, polyamide, that though is fossil-based, it also didn't exert any toxicity to these organisms. But polyamide is not biodegradable, so it can last for centuries in the environment. And remember that this shift in the paradigm involves not only bio-based, but also biodegradability. So the PLA, adding to the low toxicity, they also have this advantage of being more biodegradable comparatively, for example, to polyamide, that here, though being a fossil-based, also didn't exert any toxicity to the aquatic organisms. So to finalize, next slide, please, just to conclude on the results that we obtained. So regarding the bioresins developed within Bio-Uptake, at least one of them is considered safer for the environment than the fossil-based ones, namely the ones that use bisphenol A. Regarding the fibers that were incorporated into the intermediate format, they did not induce toxicity to aquatic organisms once they are incorporated in these intermediate formats. And finally, regarding the bio-based polymers in general, they were not toxic to the freshwater organisms, contrary to the PCl that is a fossil-based polymer. So this substitution in part of the PCl by PLA is indeed an advantage. Of course, that here we always need to have these trade-offs between the functionality and decreasing the toxicity of these products. And that's all from my side. Thank you for your attention.